Okay, so were there any questions from last time? Did anyone wake you up in the middle of the night to calculate the two-point function? No. Okay, so I was, yes. Yeah. Yeah. Mm-hmm. Yes, 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 yes. Now, the interaction with Euclidean is just phi cubed. Yes. So it's zero. No, okay. So the question was the following. If I'm calculating corrections to the was it to the two-point function or three-point function? Three-point function. Yeah, if we are interested in calculating corrections to the three-point function, let's say phi at some time, phi cubed at some time, and then we are considering interaction due to a phi cubed term in the Hamiltonian, then we're going to end up with a once we consider this Cavendish contour, we're going to be computing an integral, let's say d eta prime, of some commutator of the Hamiltonian with phi of eta. Okay, that's what you get to first order. Okay, at higher orders you have to consider the right time ordering, but at first ordering you get this, and then he was saying if this is phi cubed, this would commute, right? Now here it's crucial that this is phi cubed at a different time. So it was phi cubed at the same time, it would commute, but the phi cubed at a different time would not commute, and would give you the answer. Okay. Okay, very good. Any other? At lunch, which was when do these fluctuations become classical? So people talk about these quantum fluctuations in the very early universe, and when do they become classical, and how we understand that they become classical? Well, there is a very simple way to understand that. So we started with the Lagrangian that we discussed yesterday. And we discussed the canonical momentum. The canonical momentum is 1 over eta squared d eta of phi. And we can also write it as 1 over eta cubed eta d eta of phi. And recall we were using these coordinates where the zeta metric was so we're using the conformal time coordinates, and eta d eta is just simply the derivative with respect to proper time, essentially. Okay, I'm leaving out factors of the radius of the zeta. Now, at all times, the commutator between pi and phi for each momentum mode will always be 1, right, or I. Okay, this is something that is valid at all times. However, when we measure the field phi, or we look at the field phi, we're interested in the value of phi, and not the momentum, but we're interested in its time derivative, its proper time derivative. Let's call this dt of phi, right? And what we should understand is whether phi and dt of phi commute with each other. And if they do, then we can think of the resulting probability distribution as classical. Okay, so we can assign some classical values for the evolution of phi and its time derivative, and view the initial wave function as defined in a classical probability distribution. But this commutator can be computed from the commutator between pi and phi, which is 1, and the difference is this factor of eta cubed, right? So this is of the form eta cubed. Okay? And so you see that at late times, when this decreases, this is going to 0. Okay? So at late time, when the fluctuation crosses the horizon, after a few e-foldings, in terms of proper time, this is increasing exponentially. So exponentially rapidly, this commutator goes to 0. Okay? So that, I think, it's the simplest way to understand why it becomes classical. And it also explains the cases where it doesn't become classical. So this was the answer. Okay, yeah, there is one point I didn't make, which was important for this. Sorry. We also mentioned the fact that phi, the expectation value of phi squared, of course this is going to 0, but it should go to 0 relative to the values we are measuring for phi, for let's say for phi or phi dot. And the expectation value for phi squared was a constant. Remember, it was a constant. And so this is going to 0, this is remaining a constant. Okay? That was the situation for a massless field. One could yeah. Yeah, a little later. Yeah, a little later. Yes. Yeah. Yeah. So now I'd like to discuss the case of a massive field. And if we calculate the behavior of a massive field at late times, we just simply solve the classical equations of motion. We find that that behavior goes like eta to the 3/2 plus, well, plus, or there are two solutions. One behaves like plus or minus nu. And nu, this quantity nu, is equal to the square root of 3/2 square minus the mass of the field times the radius of the sitter, or the mass of the field in Hubble units. Okay. So we see that the case with a massless field, so we set this equal to 0, this 3/2 cancels this 3/2, and we get a constant. Okay. For any field that has positive mass, this number will be less than 3/2. Okay. So for a field of slightly positive mass, so that this is still real, we'll get a decay of the field, but the decay will be of phi squared will be less than this eta to the 3/2. Okay, and becomes eta to the 3/2 when the field gets a mass such that nu is equal to 0. Right? At which point, when that happens, this becomes oscillatory. So we should probably write it like eta to the 3/2 plus I mu, and mu is the modulus of this. This is for a field whose mass. This is when nu is purely imaginary. So this is for mass bigger. Well, when this quantity is bigger than that, so masses in particular, this is true when mass is much bigger than Hubble. So the transition here between the two is whether the mass is less than Hubble or bigger than Hubble, up to this factor of 3/2, of course. And in this situation, we really shouldn't be thinking in terms of the field and its time derivative as two things we can measure and that commute with each other and that become classical. And indeed, if we have a massive field, what we should think is in terms of particles. We should think in terms of particles and the density of particles. And this factor of eta to the 3/2 is simply the fact that the particles are diluting. So for a given mode, they get created, and then these massive particles are diluted. So that's the factor of eta to the 3/2. Okay, very good. Now, there is one more thing I wanted to say about last time that I didn't have time to say last time. Yeah, that we expected to become classical, but I didn't demonstrate it here. Okay, now, yeah, we expect it to become classical because we are looking at bigger and bigger volumes, and we are averaging over more and more of these particles. So in each Hubble volume, there is some probability that a massive particle will be created. So for a massive particle, the expectation value of phi has a factor of e to the m over h, which is the probability. Well, this is the probability of finding a particle goes like this for large masses. And it is a handy random thing where you actually find a particle or not in a given Hubble volume. But when you average over many Hubble volumes, you expect to find a classical distribution. Okay. Now, the second point I want to emphasize was scale invariance. So we discussed this metric, the metric of the sitter space. And notice that the metric of the zeta space is symmetric under changing x to lambda x and eta to lambda eta, right? So if we make that change, the top part gets multiplied by lambda, and so the bottom part, so the metric remains invariant. And this is nothing else than the time translation symmetry of the zeta space that we see in the static patch, essentially. So in the static patch set of coordinates, that set of coordinates had the time translation symmetry, and it's essentially this symmetry. So this symmetry, if we think in terms of the boundary, so there is the boundary in the far future, there is eta. We can, so if you take a point from here, well, it rescales. Let's say it's at x equal to 0, so it remains at x equal to 0, but it moves its eta position. That's the time translation we just mentioned. But if you take 2 points on the boundary, it separates the points on the boundary. Okay. So, well, if you move eta forward, then it brings them closer. But if you send eta to the past, it will separate them. So if lambda is bigger than 1, it separates and so on. Okay. So on the boundary, this acts as a scaling symmetry of the boundary points. So, and if this is a symmetry of the problem, we expect that anything we calculate here at the boundary of the zeta space should also have the symmetry under rescaling of coordinates. And this is especially true for things that become time independent. So if you are calculating something that becomes time independent, it better be also independent under scales, because it should be invariant under the isometries of the zeta, and therefore it should be scale invariant. So in particular, if we calculate the late time behavior of the 2-point function, so let's say momentum space, we saw that this became constant independent of eta for eta going to 0, and the function of k can be determined again by scaling symmetry. So the field phi, so it's scale invariant, but when we do the Fourier transform to go from position space to momentum space, so each of these factors involves a Fourier transform of this kind, and when we do that, we get that these transforms under some factor of lambda, and that is the reason why under scale transformations, this whole thing should transform like 6 factors of lambda. If x transforms in this way, k goes like k over lambda. Okay, so we'd better get a lambda cubed here. Now we have a momentum conservation delta function of this kind, and then so this produces 3 powers of lambda, and we need 3 more, and that was the k cube that we had calculated yesterday. Okay. So this is the scale invariant answer, and so we could have written this down based on symmetries without solving any of the equations. So we would have been able to do that. Of course, by solving the equations, we also got the right coefficient in front, which is h squared. I mean, this formula, another way of interpreting this formula that I didn't mention yesterday, but let me also mention it now, is that as you cross the horizon, the field phi finds itself in the thermal state of, let's say, the static patch, and so there will be some random fluctuations of the field phi. Phi has units of energy, and so its typical size of fluctuations will be of order the zeta temperature, which goes like h. Of course, this argument doesn't tell you exactly what the numerical factor is, but it gives you the right dependence. Okay. Now, besides this symmetry, the zeta has extra symmetries, which are the symmetries of conformal invariance. So also special conformal transformations. They act as special conformal transformations on the boundary. So on the zeta, they are just some of the isometries of the zeta space. To understand all the isometries of the zeta space, the simplest way to do it is to think in terms of the hyperboloid that Lenny talked about. So we had this hyperboloid. You always remember. Okay, so we had this hyperboloid that Lenny talked about. I forget now whether it's plus or minus here. It's plus, yeah. Okay, and this has this SO1 for symmetry that rotates all these coordinates, right? So we have 5 coordinates in total. So one constraint we have for the 4 coordinates. And this is the group that rotates, well, leaves this equation invariant. And this equation is embedded in R1, 4. Okay? So with the metric of R1, 4, so it's also a symmetry of the metric. And some of the ones that are manifest in that equation are the rotations. So if we can find here a subgroup which is SO11 times SO3. That's the rotations that are manifest in that way of writing the metric, rotations. This was the dilatation. And in addition, we have the off-diagonal elements, which are the translations that are obvious in the metric. And then we also have the special conformal transformations, whose form I won't write explicitly, but they are also symmetries of calculations that we do in the zeta space. Okay. Well, maybe I should write them more or less explicitly. So they are transformations where they are characterized by a vector in the same way that translations are characterized by a vector, and they are of the form of this form. So a delta xi changes in this way, plus or minus some coefficient, factor of 2 that I don't remember, times xi. Okay, so it's translations, recall, are given by a vector, so that has no x dependence, and we have dilatations, which an infinitesimal dilatation is given by, let's say, lambda x, where lambda is very small. Okay, so this has 1 power of x, this has 2 powers of x, and this all together form the conformal group. And these symmetries, well, constrain the 2-point function. So already by using dilatations, we determine the form of the 2-point function. It is also invariant under the special conformal transformations. When you look at 3-point functions, then the special conformal transformations impose more constraints than just dilatations. Okay. Okay, so last time we discussed a bunch of the zeta calculations. One of the points there, let me recall a couple of points we discussed. First, we discussed the fact that quantum field theory in the zeta is well defined and defined by this analytic continuation from the sphere. The second point was the calculation of the 2-point function of expectation values of, we could calculate Bunch-Davies or Hartle-Hawking expectation values of the field. And this could also be calculated in terms of finding first the wave function as functional as a function of the values of the field phi of x. And this was an overlap between the state phi of x, where the field has some profile, and the Bunch-Davies vacuum. Okay. Now, at lunch I was asked whether the Bunch-Davies vacuum is a vacuum, or in what sense it's a vacuum, because we have particle creation and so on, so therefore the state changes as we evolve. Now, so the Bunch-Davies is a state, and it's the adiabatic vacuum in the past, but we can use the Hamiltonian to evolve it to any other point in time, and so the zeta invariant state is this Bunch-Davies state. Okay, so we are not changing the state. This is the state, and it's given by evolving from the adiabatic vacuum that we had in the very far past. Okay, so that's what we are doing here. We are taking the overlap or looking at this state in a sort of position basis, or in a basis where we specify the profile of the field. If we have this wave function, we can calculate this by taking the integral over all phi's of the square of the wave function. Okay? And we also said that this wave function can be calculated in terms of a classical solution. And this classical solution was a solution of the equations of motion. The equations of motion were simply r mu nu equal to, let's say, some constant, let's say 3 g mu nu. And with certain boundary conditions, well, if it is the case of the metric, the boundary conditions is that the metric is some metric at the boundary at theta equal to 0, and that there was a positive frequency boundary condition at theta going to minus infinity. Okay? And we also discussed the fact that this boundary condition is naturally implemented by thinking about in the eta plane, we can just rotate the contour slightly into the complex direction. Okay. Okay, so now let's ask what happens. So if we were in flat space, this rotation of the contour certainly, well, should also be done in order to select the right vacuum. But we often, in flat space, do a complete rotation where we rotate it all the way 90 degrees, and we go to the Euclidean theory. So we can consider the quantum field theory in Euclidean space. Okay? What would happen if we did that here? So if we imagine we rotate this contour completely, and we go to the Euclidean theory. Well, so what was this rotation? So this is the eta complex plane. So this line is eta equal to IC, where C is a real number, okay? Real and positive number. So the metric that we had over there under that continuation would become dc squared plus dx squared over minus c squared. So let me put this overall minus sign. So up to this overall minus sign, this metric here is just the metric of hyperbolic space. This is sometimes also called Euclidean ADS space. Now this overall sign, so if I had put the radius of the zeta in the original formula, so we had the radius of the zeta square here multiplying everything, and so we could view it as also analytic continuation in the square in the square of the radius. So we change from r to IR. Okay, so so clearly, since the two are related by this simple analytic continuation, it's clear that the computations on the two sides are also going to be related in a simple way. And we're going to state a little more clearly in a second how they are going to be related. But for the time being, let's view this as some motivation for studying gravity in anti-de Sitter space. So from now on, I'm going to describe a few features of gravity in anti-de Sitter space and the kinds of calculations we can do in anti-de Sitter space and interesting things we can say about gravity in anti-de Sitter space. Yeah.
About point 1 and 2, is are two only in the Sitter, or in general, very accelerating universe, can they do the same thing?
Yeah, yeah. No, this can be, yeah, this can be done in both cases. Yeah. This is just a statement, the statement that we can calculate expectation values by calculating wave functions. It's a completely simple statement. The reason I'm making this statement is simply because then we'll find that this wave function is going to be simply related to the anti-de Sitter calculations. Okay. While the other one is not going to be, well, it will be related through that formula, but not in such straightforward way. Okay, so anti-de Sitter is the same, Euclidean anti-de Sitter is the same, it's given by the same equation, the same symmetry, but instead of this plus sign that we have here, we have now a minus sign. Okay. So now it's completely, so because we changed the sign, now this will be a completely Euclidean space. All the directions will be space-like. And we'd like to understand what kind of computations we can do there. Now, recall that in the case of inflation, we were interested in doing calculations that involved setting boundary conditions in the future, or considering configurations in the future where the metric had some fluctuations, so had different shapes in the future. So we could do the same thing in ante de Sitter. We could consider putting boundary conditions in the boundary of ante de Sitter. So again, ante de Sitter has the same type of diagram. We can draw a similar diagram as for de Sitter, where now this is a spatial direction, and we have again all the x coordinates here. We have again the boundary. It's not a boundary in time, but it's a boundary in space. So this is spatial direction. Sometimes this diagram is rotated, but I'll keep it this way to make the analogy more clear. And we could consider the situation where the metric in the future, instead of being the flat metric on the spatial three-dimensional surface, is some other metric, G3. So we specify a three-dimensional metric. Let me call it GB. So this is the metric at the boundary. It's a metric in 3 dimensions. So this is a three-dimensional metric. And then we can say, well, let's find the solution, or have a space which obeys Einstein's equations with a negative cosmological constant. So that is r mu nu equal to minus now 3g mu nu. That has this three-dimensional metric as a boundary. Well, first of all, there are mathematical theorems that ensure that this can be done, at least if the fluctuations, if the metric doesn't differ too much from the metric of flat space. And in fact, one can write the metric as dc squared. So there is a special gauge in which we can write the metric, where we can write it in terms of the metric on three-dimensional slices, which depend on x and c. And we can then do an expansion in c. So we have some term that goes like this, and then we do an expansion in c, so an expansion around the boundary. So there is the second term, and third term, etc. Okay. So the form of this expansion is just simply given by expanding Einstein's equations. So these equations around c equal to 0. So that when you do that expansion, you find the linear term here in c is not present. This term of order c squared is multiplied by this function g2, which is given by a local expression in terms of g0. So roughly speaking, this g2 is like the Ricci curvature of g0. And then here you get a new function that cannot be determined locally in terms of the boundary condition, but depends on the whole solution. So in order to find it, you need to find the full solution of the problem. You need to somehow close off the space in a non-singular way. So here we have all these fluctuations. And as you go into the interior, we want the space to close off in a non-singular way. This is the analog of saying that, so in the approximation where we look at linearized fluctuations, we are saying that the fluctuation should die as we go deeper into the interior. So as you go deeper into the interior, fluctuations, so if we did a Fourier model analysis, they should decay in this way. Okay? Recall the same condition we had here when we rotated the contour. Okay, so the demanding that this Euclidean space is non-singular in the interior determines a unique solution to the equations with G0 as a boundary condition. So in order to solve the equations, we need two boundary conditions. there is one boundary condition setting the value of the metric in the future, and there is a second boundary condition which tells us that the fluctuations should die in the interior or that the space should be non-singular. I mean, if you just solve the linearized equations here very deep in the interior, you will get two possible solutions, and we are setting this one to 0, so that's the second boundary condition. Okay, very good. Then we can take this solution that we found and insert it in the gravitational action, so the Euclidean action for gravity. So that is e to the minus m squared, now the radius of ADS squared, and then the Euclidean action. So the Euclidean action is minus square root of GR, minus 2 lambda, and well, in these conventions we've set lambda to 1 and absorb lambda into the radius of ADS. And then there is some extrinsic curvature term. So this is the action of gravity with fixed boundary conditions. Now you can evaluate it, and when you evaluate it, you find, I guess I need probably a bigger blackboard. When you evaluate it, you find infinity. Okay? Now, why do you find infinity? This could be tricky. Well, you find infinity basically because the curvature is, if we calculate the scalar curvature, we get something proportional to the metric. So the square root of the metric, we put it back in the action. It's negative, but it doesn't cancel the 6. It actually gives another minus 6. And so we're calculating essentially the volume of this space. But the volume is infinite because it's for the same reason that the volume of the zeta space is infinite. It's the same 1 over eta square we had in the metric. We have 1 over eta, 1 over c squared. It's the same thing. OK, so let's calculate not the volume, but the volume up to some c equal to epsilon. OK? And see what this looks like. And so we now calculate this Euclidean action. And what we find is that there is a term, well, everything, at least in this classical limit, is proportional to the Planck scale. And there is a first term that, with a plus sign, goes like 1 over the volume of the boundary, essentially. Proportional to the boundary metric. So this is an integral over 3-dimensional space. Now, this is easy to understand. So, I mean, we're calculating just the volume, even for the case that the metric is just 1. Let's calculate that in that case. So we're calculating the volume, and we have a dc over c to the 4th. And then we do this integral from epsilon to infinity. At infinity, there is no contribution, and we get the 1 over epsilon cubed. Okay? If we wanted to understand the sign, then it's important that we had the extrinsic curvature term. Actually, the positive sign comes purely from the extrinsic curvature term. Then there is another term whose coefficient, whose sign and coefficient you don't remember. And I'll tell you how to determine these signs and coefficients in a second. GB times the curvature of the boundary. So this is the curvature of the 3-dimensional boundary. This is a 3-dimensional curvature. So there are these two terms. And then there is a finite piece. Now, the finite piece cannot be written as a simple function of the boundary metric. In order to calculate it or to find it, you really need to solve the whole problem. And it's a non-local function of the boundary metric. So here, these are completely local functions of the boundary metric. And in particular, notice that something that will be useful a little later, but let me mention it now. So there, we made an arbitrary separation here between epsilon and this boundary metric. So if we go back to the original expression, we could say, so we had the metric c squared plus gij divided by c squared, right? And so we can say that, but the full boundary metric, the complete boundary metric in the 4-dimensional space is actually this whole thing at c equal to epsilon, okay? Up to some small corrections here. So notice that we could rewrite this in terms of this full physical, if you wish, boundary metric, and we would get that this is just the volume of the boundary. We would put the epsilon inside. Again, here we could put the epsilon inside. And these two pieces are pieces that depend on epsilon. And in particular, we could view epsilon as an overall scale of the metric. They depend on the overall scale of the metric. This piece here is finite and independent of epsilon. So it's independent of how we divide the metric and epsilon. And in particular, we could have chosen, for example, an epsilon that depends on x, so some cutoff that depends on x, different slicing. All these terms will be of the same form, except that the epsilon will appear here inside the integral, cube. And this whole function is just nothing else than the physical metric that we got here. So these terms depend on the actual value of the volume. These finite pieces are independent of how we slice our space. Again, that is the scale invariance of the fluctuations we mentioned before. It's the same thing, the same scale invariance. And, well, it actually implies the scale invariance we discussed before. So this is something a bit bigger, which is the conformal invariance of the answer. So we get that this finite piece is invariant under changes of the boundary metric by overall factors that could depend on x, right, but not on the indices I and j. So if we rescale the metric completely, this finite piece will not change. So this is saying that this finite piece, whatever it is, depends not on distances on the boundary, but on, let's say, angles and geometry of the boundary. Okay. So this is the type of transformation that preserves. So if it well, changes distances but preserves angles. Okay, now, so that's something you can calculate. And so you can define so this you can calculate classically, but in principle you could also compute quantum corrections. So you could imagine taking such a metric and then quantizing the field around this background, so doing the one-loop integrals. And then you will get a correction to this formula. And again, there will be pieces that will be proportional to the volume. Well, first of all, there will be the UV divergences in that theory. So you first renormalize in the bulk the UV divergences. And then there will be such, these divergences in epsilon are infrared divergences in the bulk. So in the bulk, we get these divergences because we are integrating over an infinite volume. But for the one-loop corrections, we also expect that similar volume factors with perhaps different coefficients. In fact, at the one-loop level, we don't expect an overall mR² coefficient, but a coefficient which is of order 1. So it's just the contribution from the one-loop determinants. And as we approach the boundary, those one-loop determinants can be expanded in. So one of the key things here is that we are considering metrics on the boundary which have some scale of variation, but we take the epsilon to be much smaller than the scale of variation of these metrics. So locally, the space at each point will be very close to empty, well, or completely uniform hyperbolic space or Euclidean anti-zeta space. And so we'll get the contribution that is proportional to the cutoff, which is coming from distances very close to the boundary, will be that we essentially had in empty anti-de-Sitter space. And that's why we're getting these factors of the volume, and we expect to get, again, these factors of the volume to all orders in perturbation theory. Okay, so that's what we get in gravity. Now, so we could define this partition function, which is this full thing. This is sometimes called the gravity partition function. It would be the sum over all geometries that end on that boundary, including quantum corrections and everything. And this can be done perturbatively, in principle. In a string background, it could be done. There are some solutions of string theory where, in principle, this could also be done, so in a complete quantum gravity theory. And we can write it as some divergent piece, so the piece that is infrared divergent, times some finite contribution, times C. This is sometimes called renormalized. This is, from the bulk point of view, is an infrared, is throwing out some infrared divergences and keeping, so it's a renormalization of infrared divergences of the metric. And in principle, the same could be done if you had scalar fields, fixing the values of the scalar fields at the boundary and so on. If the scalar fields are massive, it's a little more subtle, but it can also be done. Okay. And this object, whatever it is, should be invariant under these Weyl transformations of the metric. Okay. Now, such functions. So these functions. So a way to generate functions of the metric that had that property is to consider a quantum field theory on that metric. So let's say a three-dimensional quantum field theory on that metric that has some fields. Let me call them psi's and let's say a. So some functional integral over some fields in 3 dimensions. And then we have some action, square root of g, where this is the 3-dimensional metric over 3 dimensions, and some action with these fields. So we could have some fermionic fields, bosonic fields, f squared. Let's say A is a gauge field. So we can have actions of this kind in Euclidean space. And if we do this functional integral, we'll get some function of the metric. Okay? And this function of the metric is called the partition function of the field theory. And it will be invariant under that Weyl transformation if this field theory is scale invariant. So if this is a 3-dimensional scale invariant theory, we'll get a function of the metric which is Weyl invariant. And again, if we consider small fluctuations around flat space, we'll have scale invariant fluctuations. Okay, very good. Now this function is also in the field theory language is known as the generating function for correlation functions of the stress tensor. I mean, imagine that this metric was the flat metric plus some small fluctuation. Then something we could do is we could write the original action as the action in flat space, so the flat space action, plus the integral of hij times the stress tensor of that field theory. So I guess I'm writing too small here, right? Yes. Yeah. Yeah, so we could write this action as the action with the metric, with the Minkowski metric. So let me call it S0. Just this is the action in flat space, flat 3-dimensional space, R3, plus the integral of the stress tensor of the 3-dimensional theory times hij. Okay, the small fluctuations. To first order, we could write this. And then we could take it's a bad idea. Oh. I guess the whole point is this one should be in the front. No? Okay, let me leave it here. Let's move to another blackboard. Yeah, I should use these bigger blackboards. Let's see. Now, okay, now if we took this C and we took derivatives with respect to h, ij, let's say we take 2 derivatives for the sake of this argument, and then we set hij to 0, that will give us the same as taking the 2-point function of the stress tensor well, these indices are not sum order. This is ij and kl. So we get t ij t kl at, let's say, one position. This is some point x and some point y. Point x and y appear here. So we take the derivative with respect to the metric at point x and point y of this partition function. Okay? Is it clear what we're doing? So we're taking a flat space, and we are making a small change in the metric at x, a small change in the metric at y, and we are computing this correlator. This angle bracket here means a correlator in the CFT. Okay? So we take the conformal field theory, and we do this correlator. And if we take the partition function of the conformal field theory, and we calculate this variation with respect to the metric, we get this two-point function, and so on with n-point functions. Okay. Now this is something we can certainly do at the level of CFTs. And this is an example of how you would calculate in practice, if you wish, this function of the metric. So you could start from flat space and calculate it perturbatively in this way by considering small fluctuations of the metric. Okay. Now the ADS CFT correspondence says that for any consistent quantum gravity theory in ADS, if you do this calculation, so the calculation of either you can think of it as the wave function in the far future, or sometimes called the partition function, this is the same as the partition function of some conformal field theory, some consistent, reasonable conformal field theory that is defined on the boundary. And there are some examples of this relationship that involve concrete ADS compactifications of string theory and concrete conformal field theories on the boundary. Okay. So I won't go over these examples too much, except to say that using the field theory, we can compute, in principle, given enough computer power, we could in principle compute these wave functions to any order in the, or we could compute them to any order in m times the radius of ADS. So there is some expansion parameter which is 1 over m times the radius of ADS. That's the expansion parameter for gravity both in de Sitter and anti-de Sitter. That's the dimensionless effective expansion parameter that we have in both cases. And we could calculate this object. And well, the leading order term, we already saw how it depended on this parameter. Times the finite piece we were talking about. So we'll get this CFT after we renormalized on both sides. We extract the divergences. So the things that look like, the CFT will have some UV divergences. And so this partition function has some UV divergences, which are of a structure similar, identical essentially to the one we wrote over there, except that epsilon is a short distance cutoff. These divergences in the field theory are not universal. They depend on what cutoff you use. And this relationship, this equality, holds, as far as we know, only for the finite piece. So we don't know of a precise relationship between the two cutoffs. So there is some cutoff we use in gravity, and there could be very, very different cutoffs we use in field theory. We don't know a precise correspondence between the gravity cutoff and the field theory cutoff, even whether there is, in principle, a precise correspondence. Anyway, so this is the first term times that finite classical term. So let me call it F0. And then the one loop correction will give us some F1. And then two loop corrections will give us some F2 and 1 over that effective expansion parameter, et cetera, et cetera. Now, in quantum field theory, this expansion parameter in many of the examples is related to the rank of some gauge group. So this, in many examples, is well, in all examples, is a gauge theory. Well, not all examples. So in most of the examples, it's a gauge theory. And with gauge group UN, let's say, or SUN. And in such gauge theories, one can do a large n expansion, and one has an expansion of this kind where this quantity is proportional to n squared. This is independent of 1, and this is 1 over n squared. Now, the reason we have that expansion is that, well, maybe I shouldn't go into all these details, but let me just say the basic reason, and very quickly, is that we can expand all the Feynman diagrams of the gauge theory into what are called planar diagrams, which give us this main contribution, and then diagrams that you can draw on a genus 1 surface, which correspond to this, and so on. So, said in a quick way, just an analysis of the planar diagrams, not a very sophisticated analysis. If you want, I can go. Well, I could go over it if you are willing. That simple analysis ensures that we have this type of expansion in the large n gauge theory. And we identify this leading order term with the classical contribution we get from gravity. Are there any questions? No. That's dangerous. Okay, that is very dangerous. Is this not concrete enough, or no? Let me.
We wrote down a partition function.
Yes, yes.
In terms of a functional integral.
Yes.
That's an ansatz, or we've shown that to be the case?
Well, in a part, yeah. So this is the partition function of the CFT is equal to that. That's simply the definition of what this is. The non-trivial equality here is this one. That is that the gravity, what we were calling the gravity partition function to all orders, was equal to a CFT partition function. And in order to make this equality precise, you need to say exactly what gravity theory you are considering. I was here considering just purely Einstein gravity. And that theory is not well defined because, first of all, it has the UV divergences, and you have to supply the counter terms. So you have to define it by saying what all the counter terms are in principle. Or you could define it through string theory. So the examples we really know are examples where the gravity theory is defined as a particular string theory compactification. So a particular point on the string theory landscape where we have a negative cosmological constant, and we sit at that negative cosmological constant value, at least at infinity, asymptotically. And that defines completely this partition function. Right? That's the left-hand side. The right-hand side is defined through that formula with some particular quantum field theory. Well, maybe I just let me mention one example so that. So I mentioned an example in 4 dimensions. So there is a particular theory that you can get, particular 4-dimensional gravity theory that you get by taking a 11-dimensional space, which is ADS4 times S7 divided by CK. Okay, so this is ADS4 times S7, and there is some quotient here. Let me ignore the quotient for the time being. Let me be sloppy. Yeah, are you?
Yeah, I don't have a question. I have a pedagogical, strictly pedagogical comment.
Yeah.
That might be helpful to some
Yeah.
people, or that you might want to
Yeah.
comment on. The thing you're calling the wave function here
Yeah.
is not really the wave function that you would use if you were doing quantum mechanics in ADS space.
Yes.
It's a wave function which where you propagate outward in
Yeah.
space rather than in time.
That's right. Yeah.
Some people might be confused about that. I thought maybe it's just
Oh, good. Yeah. I was, yeah. Okay, for the moment, let me call this the partition function. We'll see, we'll discuss later how in what sense it can be viewed as a wave function. If that was confusing, let me not call it a wave function for the time being. Or let me call it a wave function the same way that we called it before, e to the is as a path integral up to some position. It's a function. So it's, I never talked about yeah, normally this is called ADS, where this ADS space is with Lorentzian signature. I'm mainly talking about the case where we have Euclidean signature. And if we are dealing with the problem in Euclidean signature, this is the natural thing to compute, and it's these partition functions. In Euclidean signature quantum field theories, we similarly compute such partition functions. You can view them as problems in statistical mechanics. So we have a problem in statistical mechanics. We compute this partition function. Very good. Now, oh yeah, I was going to discuss one example. So there's this example. And in this example, the dual, so this is M theory on this space. So it's a particular version of string theory. The strongly coupled limit of string theory is M theory. It's 11-dimensional. And we put it on this space. We get a well-defined theory in ADS4. In this case, this is a compactification where these two radii are comparable with each other. So it's really, in some sense, locally looks like 10-dimensional space. But when you go to very long distances, the volume of this space grows while this one stays constant. So there is a sense in which we can think of it as a 4-dimensional situation. And in this case, the dual theory is some particular 3-dimensional theory that has a gauge group un times un. And it has a bunch of fermion fields and bosonic fields that transform in the fundamental under one gauge group and the anti-fundamental of the other. And of course, we have the complex conjugate ones. Okay. And then we write an action for this, and we impose that it has a maximal number of possible supersymmetries, and that defines the theory uniquely up to an overall constant. So the theory has some, in 3 dimensions for gauge fields, you can write a so-called Chern-Simons coupling. So there is a Chern-Simons coupling for each of the 2 gauge groups, and you can write it in this way. And this is a, if we only had the gauge field, this would be a topological term. However, once we put the matter, we get some non-trivial interacting theory. And then, if k is large, the theory is very weakly coupled, and that corresponds to the case where we divide here by ck. When we have the full S7, we just take k equal to 1, and that's the strongly coupled, the more strongly coupled version of this theory. Anyway, so that's one particular example, and you can do computations using this example and compare them to gravity computations. An important point is that whenever the gravity calculation is weakly coupled so that we can trust the gravity approximation, the field theory will be strongly coupled. So it will be difficult to do calculations in field theory because the coupling will be large. So we saw that here, that at k equal to 1, that was a strongly coupled field theory, for example. So that's a general feature. But thanks to the fact that many times, thanks to the fact that we have supersymmetry, we can actually do calculations in this strongly coupled field theory. And a calculation I would like to spend a little time on is a version of this calculation where we consider the calculation when we have an S3 boundary. So we discussed so far the case where we have a flat boundary plus some small fluctuations. Let's now consider the case that we have an S3 boundary. So in this case, we can fill it in. And we just fill it in with empty Euclidean ADS space or hyperbolic space. And the metric that fills it in is very simple. So it's d rho squared plus sine squared rho d omega 3. So for very large rho, we are close to the boundaries. This is rho equal to infinity. And here where the S3 shrinks to 0, that's rho equal to 0. So the whole space shrinks to 0 in a smooth way. Okay? And we can calculate that finite piece. And let's just describe the calculation. I gave it as a problem to do it in detail. So we calculate up to, so the naive thing would be to calculate to infinity d rho of the Einstein action. And the Einstein action is just the volume, as we mentioned, so the volume of this space. This will be a sine rho cubed. Okay. Okay, so times some angular factors I'm not going to keep track of. So there are some constants that correspond to the angular factors. So what are we computing here? So we're computing the on-shell action. So the on-shell Einstein action, so up to some constants, is equal to this integral. It's infinite. We regularize by putting some rho cutoff. And of course, the leading order terms, most divergent terms go like 3 rho cutoff. So that's the term that has, we expand this exponential and we get various terms. And then there will be a term that goes like rho cutoff. And of course, when we do this integral, we'll get some cosine hyperbolics at some point. And those cosine hyperbolics, when evaluated at 0, at some point they will give us some constant value here. Okay? So that's the form of this answer. As an exercise, gave it to calculate this constant. So that's a concrete calculation of that finite piece we discussed there at leading order. So that's what, in this particular example, this F0 would be just a constant. So this finite, this is not the divergent piece. This is just the finite piece. It's some constant proportional to m times radius of ADS. We can express that constant in terms of the parameters of the field theory. And then we can ask whether we can calculate that same constant using the field theory. And the answer is yes. So we can actually define the partition function of a field theory on S3. So this partition function we were talking about here, we could take the case that the metric is on S3. And at first sight, it looks like it might not be well defined because of the UV divergences. There is just one thing we're calculating. There is some divergence, how I'm going to extract the finite answer. But the point is that this is actually well defined because divergences are all local divergences of that kind, and we can calculate them as a radius, as a function of the radius of the sphere, and then we'll get a finite piece that that is what we are defining as the renormalized value of the function in S3. And if you can check that you indeed can do the calculation if you had a field theory that is weakly coupled, and for a weakly coupled field theory or a free field theory, you can certainly do the calculation. Now, it's more surprising that you can do it in the regime that the gravity theory is valid. So that will be a strongly coupled field theory, and there is relies on some magic of supersymmetry that allows you to actually do this computation, and people have done the computation, and they found an answer which indeed agrees precisely with this result we computed in gravity. Okay? We computed here a constant with some pi's and 2's and so on, some sine, everything. Everything agrees precisely with the calculation, the same calculation in the field theory. Okay. So now let me discuss a little more this is an art. In principle, there is a unique. Well, there are dualities in field theory. It might be that there might be different dual formulations, but in principle, there is a unique field theory dual to some gravity theory. So the standard technique for finding the simplest one is the following. So you the simplest one is to say that you have some branes in the in some number of dimensions. Let's say we have two-dimensional M2 branes, 2 branes. So 2 branes. These are objects that have a 2 + 1 dimensional world volume. So they're extended along 2 spatial dimensions and 1 time dimension. So we have these M2 branes in M theory, so in 11 dimensions. And then we need to figure out what field theory lives on these M2 branes. What field theory describes the low energy fluctuations of these M2 branes. yeah, maybe this was an example related to that, but it's an example where the field theory is a little less clear. Let me do the case of D3 branes. So we are in now 3 + 1 dimensions, and we are in 10-dimensional string theory. So we have these objects that have a 4-dimensional world volume and an R 1,9 space. So there are 6 dimensions that are transfers to the branes. So in those 6 dimensions, the branes look like a point. So this is in the transverse R6. Okay. And now we look at the low energy description of the fields on these branes. Now, in this theory, there is a coupling constant in the bulk, which is the string coupling constant. And when the string coupling is weak, we can find precisely in a simple way what fields live on this D-brane. This is called Dirichlet brane because there are open strings that can end on it, and the massless modes of these open strings are gauge bosons. So A mu, they are gauge bosons, and well, I guess there are obvious fields that live on this brane, which are the transverse fluctuations. This it's very clear that these fields will be massless, and they are simply the Ghoston bosons for the broken translation symmetry in the extra dimensions. So we have 6 such gauge bosons. Okay. Let me try to explain the derivation of the field theory without going to the details of string theory. So we had the 6 bosons, 6 bosonic directions for a single D3 brane. And then we also know that this brane preserves a certain number of supersymmetries. So we had some supersymmetries in the 10-dimensional space. So it preserves supersymmetry. Supersymmetry is a symmetry that relates bosons and fermions. And so if we had these scalar fields, there should be some fermionic partners, so chi alpha. And it turns out that supersymmetry also, in this case, we have so much supersymmetry that it also generates some gauge bosons that live on the brane. Okay, that's for a single brane. So this would be a U1 gauge theory. And now you would like to consider many branes. So certainly, if you have many branes, this field, at least when they are separated, you have n of these fields, n phi i's, and n of these U1 gauge fields. And the question is, what happens if you brought all these branes together? Certainly, now you have some symmetry under exchange of the various branes. So you expect to have some kind of permutation symmetry of the branes. But actually, you have a gauge symmetry. So this permutation symmetry gets enhanced to a full gauge symmetry. And this is something you can see also from the string theory description very directly. And so in the end of the day, you get the same spectrum. But now each of these fields is an n by n matrix. And you have an action for these fields, which starts with the ordinary Yang-Mills action for the gauge fields. And, well, blah, blah, blah for the rest. Okay? So it is completed in a unique way by supersymmetry. So there are kinetic terms for the scalars, the fermions, some interactions determined by supersymmetry. Okay, so those are just simply a description of the field theory living on these branes. I discussed it in detail in this particular case, so we can find it in detail. And then you can also notice now this brane is an object that has some tension and some charges. Well, let me discuss just the tension. It has some tension, and it curves the space around it. So it will curve. If we look at this space, so it was like a point naively, but when you take into account the fact that this is an object which carries some tension, it will curve the space around it, and you'll find some solution which looks like a black hole. So if you forget about all this D-brane description and you look at it from far away, it's an object which carries some charges and some flux. It generates some fluxes under 5-form potential. So there is an S5, and there is some flux on that S5, which is quantized to be n. And you get this extremal black brane solution. And this extremal black brane solution has a geometry which, very close to the horizon, looks like ADS5 times S5. Okay? So that's where the ADS5 times S5 came in. And now you need some argument that relates these two things, that relates the field theory we discussed here in the beginning from this brane picture and this ADS5 cross S5 region. And that argument is that if you started with these brane configurations and you went to very low energies, so at high energies you have all these string modes, etc., etc. But at low energies, you only have the field theory modes on these branes. And these field theory modes are described by this field theory. And they are weakly coupled to gravity in the bulk. And at low energies, the gravity theory in the bulk becomes essentially free at long distances. And also the coupling to the brane modes disappears. Now, if you look at this picture and you try to take the low energy limit of this picture, well, if you are far away, okay, the low energy limit far away from this object looks similar to what it looked here. You have free gravity, essentially. But now an excitation that is in here, inside this throat, is subject to a redshift. So this is like a black hole horizon. As you bring it closer and closer to the horizon, its energy, as measured from an observer far away, will be smaller and smaller. And so if you put some cutoff on the energy, so let's say some low energy cutoff corresponds to a very long wavelength mode outside, inside, it could be a very short wavelength mode, smaller than the radius of this space, but very, very deep inside this throat, so that it has the same energy as this very long wavelength mode. So you have all these low energy modes that live close to the horizon. And in both pictures, we got two decoupled theories. So in this case, we had the field theory living on the brane, which was given by this Lagrangian. On the other hand, we had all the low energy modes that live here in ADS5 cross S5 very deep inside the horizon. And so it's natural to conjecture the two are the same. So that's where the motivation for this relationship, and also the method for finding the precise relationship. So the method is to find the brane configuration, find its near horizon geometry, and independently find the field theory living on the branes. So this method requires a bunch of things that you should be able to do. So there are many situations where we can find the near horizon geometry but cannot find the field theory. There are some situations where we can find the field theory but not the near horizon geometry. And in happy situations, we can find both, and then we have a dictionary. But we think that in principle it should hold even if we can't find it in a very direct way. So yeah, so this is basically the method. Okay, I missed some pages. Okay, now let me discuss in what sense this is a wave function a little more. So for that purpose, it's useful to go back to the well, before I discuss that, let me make the comment that this calculation that we did here is very, very similar to the calculation of Hartle-Hawking for the wave function of the universe and that probability. So let me try to make the similarities a little more manifest first for this wave function, and then I'll discuss some more issues related to the, in general, to the wave function. So we had the metric there of ADS. Let me just copy it here. D rho squared plus sine hyperbolic squared d omega 3 squared. We had d tau squared plus cos squared tau d omega 3. This is ds. This is Euclidean ADS, or hyperbolic space. Okay. Now, if we had here the tau plane, there was a picture that we discussed last time where we were calculating the wave functions or probabilities at very large tau, so tau much bigger than 1. And we were integrating, in order to find it, we were integrating along some contours, which came here to minus I pi over 2 and I pi over 2. And this line here was the line describing an S4. Okay? And we discussed the fact that if we wanted to calculate the wave function, for example, e to the I s as a function of the boundary metric in the de Sitter case, what we did was to put some boundary conditions here at large tau, and then find the solutions with the boundary conditions that the fields decay when we rotate the contour just a little bit here. And that in fact, that was the description here in the Poincaré patch for very large tau. Now, when we went to the global picture where we had the S3, the correct prescription, or one prescription, was to analytically continue here to the sphere that shrinks to 0 size. Okay, so this contour corresponds to having a hemisphere and then the Lorentzian, the zeta space growing from the S4. Okay. Now, okay, we're doing this calculation along this contour. Now, we can notice also that imagine now we took this contour, okay? This corresponds to a value of tau where we have I pi over 2 plus rho, okay? And you can check that if we take this, this value of tau and we insert it in this equation, we get minus this metric, okay? So they're very closely related. So the calculation we just did, that calculation gave us some constant, that constant at the end, that is essentially the same constant that we would get by doing the integral over this contour. I mean, the only difference is that we change the overall sign of the metric, which again can be absorbed by an overall sign of changing the radius of ADS to I the radius of ADS. Okay, up to that change is exactly the same calculation. Now, the calculation of the path integral with this contour, what does it give us? So as long as we are evolving the metric along here, we get something real for the action. But when we make this the integral around here, we get half of the action of S4. Okay? And so half of the action of S4 is e to the entropy of the zeta space divided by 2. Okay? Don't confuse S, which is the entropy, with S, which is the action. So that's that finite piece. And again, in this case, we discussed last time that we had these divergent terms which go like epsilon cube, blah, 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 but they had an I. And then we had the finite piece, which in this case will get a finite piece, which is completely real. Okay. And these two constants match exactly, including the pi's and the 2's and everything. You can check that. And they only differ by their sign. Okay? And as I said, in the case of Euclidean space, of Euclidean ADS, that constant is correctly given by these calculations. It's consistent with the ADS CFT, and you can calculate it to all orders. It's a precisely well-defined quantity, which raises the question of whether the same quantity here that we calculate in the sitter is also well-defined or not. It's very similar. It has a very similar nature. Is this the right way of calculating probabilities, or is this a good approximation to something? So we certainly in the Euclidean ADS case, certainly the exact answer was not equal to the gravity answer, but it became the gravity answer in the Larsen limit. So in the Larsen limit, the gravity answer gave us a good approximation for that quantity. Could we get the same, could this Hartle-Hawking wave function of the universe give us the correct answer for the global S3? Now, I should mention that this way of computing the wave function, of course, gives you correctly the fluctuations. The fluctuation spectrum around the S3 is correctly given. By correctly given, it agrees with the same fluctuation spectrum computed in many different ways. Okay? But here I'm just discussing the question of whether it could correctly give the probability of having a big S3 or having a compact space with positive curvature. Okay, so a little more about wave functions. And now, there is a very good reason why the wave function of the universe is viewed with some suspicion. And the reason is that it's very hard to define it precisely. So let me describe some attempts that were made to define this wave function. So the simplest is to just naively quantize the gravity theory in the canonical formalism. So you take your metric, And you could choose a gauge. Let's say, let's change the gauge n0 equal to 1 and I equal to 0. Well, I'm using, again, small letters, sorry. I hope everybody knows what n is, or ni are. Well, if not, we are just choosing a metric, which is, let's say, dt squared plus gij dxi dxj. Okay? We choose this metric, we fix some gauge, and now we can quantize the theory in this gauge. So GIJs are the metric, the three-dimensional metric is a dynamical variable in this way of thinking about it. And we can write an action for it, and we can write a Hamiltonian and so on. So let me briefly. So we can write the action and the Hamiltonian and so on. And what we find is that, well, there is the metric, and then there will be the canonically conjugate momenta. But these momenta are constrained, and they are constrained precisely because of the gauge symmetries that we have used to use these constraints, to impose those constraints. And in the end of the day, we get that the whole thing should be some wave function of Gij, and it will be subject to two constraints. One is the momentum constraint, which says that the derivative with respect to Gij nabla I is equal to 0. And this is a very trivial thing. This is just saying that the wave function, whatever it is, should be invariant under reparametrizations. So reparametrizations change the metric in this way, and this should be equal to G. Okay, that's exactly the same equation. And then there is the Hamiltonian constraint. So this general relativity is a theory that is time reparametrization invariant. And if you were to fix a gauge like this, then the equation of motion for n implies that the actual Hamiltonian is 0. And in this case, that implies a constraint on this wave function, which has the form roughly delta j. So there is a term like this. There is another term that involves the derivative with respect to the trace of the metric squared. So these are all derivatives with respect to the metric, and then there are some functions of the metric of the form square root of g r minus r, the curvature of the three-dimensional slice. These are all three-dimensional metrics. Now integral square root of g times 2 lambda. So this is the Hamiltonian constraint at point x. Okay, these are all derivatives at point x, and they are acting on the wave function. Okay. So that, in principle, is determining this wave function. And there are a couple of difficulties with this story. Well, the first, one issue is that we're doing this at the level of gravity, and gravity is not normalizable, so we don't know exactly what we're doing. So that's one problem. But well, maybe we can imagine that in some theory of quantum gravity, some object similar to this could exist, and maybe you could define it perturbatively and so on. Or maybe even in string theory, maybe it could be defined in some way. String theory, we don't know how to think about objects like this. And okay, I'm out of time. Anyway, in the yeah, I guess I don't have enough time to discuss this issue. What? Yeah. Maybe I'll continue. Well, like, can I get 5 minutes? Or, yeah. Okay, so there are a couple of issues. So one is the one I mentioned about non-normalizability, and the second is that this equation in the space of metrics is it's more like an equation similar to the Klein-Gordon equation, sort of like dx0 squared plus dxi squared times, let's say, psi equal to 0. So we think of x0 and xi as different parts of the metric. So the conformal factor of the metric, in fact, the derivative with respect to the trace, has a minus sign similar to this, and this implies some problems and some issues. So in the case of the Klein-Gordon equation, so we know that we get these two solutions of the Klein-Gordon equation and a norm which is not positive, and this led to the second quantization and so on. So some people propose, oh, maybe we should do second quantization, etc., for the Wheeler-DeWitt equation. This equation is called the Wheeler-DeWitt equation. And in particular, the norm, so maybe I should be more specific of how the norm is defined in this case. So the thing that is the norm of the Klein-Gordon equation is an expression of this kind, dx0. So a similar norm for this equation is a little complicated because you would have to take a product of derivatives at each point of the trace of the trace of the metric. So psi and psi conjugate. So it's like having many Klein-Gordon fields, one at each point in X. So we have many time-lag directions, and so we have this issue. In the Klein-Gordon case, okay, we had one time-lag direction. Here we have one time-lag direction at each point in space. Okay. Anyway, so these are some of the issues. But if we ignore all of this and we imagine a space which is minus d tau squared plus a squared d omega 3, just considering purely the volume factor in a Lorentzian de Sitter case, then we find that the wave function that obeys this equation, so there are a couple of wave functions. So one, for very large a, they behave like a cubed e to the I a cubed plus a plus finite. And then there is another one that has the same thing with a minus sign. Okay. And each of these exponents is precisely the quantity that we were computing before. So when we were computing things semi-classically, we were computing precisely these exponents. So Harlan Hawkins said, well, maybe we can determine the wave function by doing this path integral from this path integral point of view, and then in the semi-classical approximation, we would determine these finite pieces to be the values we were discussing so far. Okay. Now, let's see what we do in ADS. What do we know about the ADS case? So we could do exactly the same thing in the ADS situation. We could write something like the Wheeler-DeWitt equation. We don't know exactly how it is defined, but let's compare the answers we would get by doing the Wheeler-DeWitt equation with what we know about ADS space. So we would find that, again, the Wheeler-DeWitt equation has two solutions. One goes like a cubed plus a plus finite. Well, let me ignore this subleading term in a. It's irrelevant. So for the discussion. So there is a plus a cubed, and there is some solution with a minus a cubed. Okay. Now, the ADS CFT correspondence tells us that the coefficient of this term, of the one that goes like plus a cubed, is the partition function of the CFT. Okay? So this is what we were calling the psi, or the C renormalized. And this is the quantity we are computing through ADS CFT. So we don't know whether the Wheeler-DeWitt equation makes sense or it doesn't make sense, whether it can be defined in the full theory or not. But something we do know is that if we take the limit of the Wheeler-DeWitt, of whatever, of some object like the Wheeler-DeWitt equation, at least the limit when a goes to infinity, when the size goes to infinity, that is well defined. And it's well defined in this way, that the coefficient of the diversion term when a goes to infinity is the partition function of the CFT, which is something we can calculate. Okay? So one could wonder then whether whether the same could be true in the de Sitter case, whether maybe we cannot compute, or it doesn't make sense to think about the wave function for finite a in a precise way, but that maybe the coefficient of the term when a goes to infinity, the infinitely oscillatory coefficient, that might make sense. Now, notice that in order to derive ordinary quantum field theory from the Wheeler-DeWitt equation, it's convenient to look at this oscillatory piece, just one term of this wave function, and these derivatives are all going to act on this leading term that is the one that gives the biggest value for the derivatives, and then the Wheeler-DeWitt equation. Here, the second order operator will get most of its contribution from the piece that oscillates more rapidly. And then we get the Hamiltonian constraint becomes the first order Schrödinger operator that we know in quantum field theory. Okay? So we go from the second order operator to a first order operator, where A is essentially time. So A, recall when we were putting the cutoff, in our previous discussion, we were putting some cutoff. We were saying the metric is some metric times 1 over eta. So here A is playing the role of time. So there is no time in the original Wheeler-DeWitt equation. So it's a timeless equation. H is equal to 0. And we get time by identifying a clock among the various variables. So in this way, in this case of the sitter, we identify the clock to be the scale factor. Okay, so let me conclude. Yeah, I went more than 5 minutes. Well, I was going to end with some discussion of what are the objections. And so the question is, can there be a DSCFT, and whether there are objections or not against that. But maybe, maybe I shouldn't talk about this now. We could schedule. Yeah. Okay. Okay, I finish here.